Preparing for a Fastly software engineer interview questions and answers interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Walk me through the lifecycle of a request through Fastly's Edge network. An Edge request typically enters through DNS steering, reaches a nearby POP, passes TLS termination and WAF rules, then checks cache before contacting origin. I would explain cache keys, TTLs, stale serving, shielding, and observability. Fastly's value comes from programmable decisions at the edge, reducing latency and origin load. I'd also discuss failures, bypass unhealthy origins, preserve error responses carefully, and use request IDs to trace the complete path. While answering, cover DNS steering, POP selection, TLS termination, WAF processing, cache lookup, origin fetching, shielding, response delivery, request tracing, and how edge decisions reduce latency and origin load. Question 2. How would you design cache invalidation for a large Fastly customer? Cache invalidation is a correctness problem, not merely a speed feature. I would use surrogate keys to group related objects, then purge by key when content changes, purge URLs for precise updates. I'd define propagation expectations, protect against accidental global purges, and monitor purge latency. For immutable assets, versioned file names avoid invalidation entirely. The design should also address stale while revalidate, concurrent misses, and what users see during origin or purge service failure. Make sure to cover surrogate keys, URL purges, purge propagation, versioned assets, stale while revalidate, safety controls, authorization, purge latency, monitoring, and behavior during origin or control plane failures. Question 3. How would you use VCL to implement a custom caching policy at Fastly? I would normalize the request in VCL RECV, decide whether it is cacheable, and construct a stable cache key that includes only meaningful dimensions. In VCL backend response, I would apply TTLs, stale behavior, and surrogate keys, while VCL deliver can add diagnostics. I'd avoid caching personalized responses, strip irrelevant cookies, and use feature flags or staged activation. VCL is powerful, but careful review matters because a small policy error can leak data or amplify origin traffic. In your answer, talk about request and response lifecycle subroutines, cache keys, headers, cookies, TTLs, pass versus cache behavior, synthetic responses, normalization, security, and testing changes safely. Question 4. What would you consider when choosing Fastly Compute for edge logic? I would move logic to compute when it benefits from proximity to users, such as authentication checks, header transformation, routing, experimentation, or lightweight personalization. I'd keep durable, data-heavy workflows at the origin unless edge-accessible storage meets the consistency needs. WebAssembly isolation provides portability and safety, while resource limits demand efficient code. I would design explicit failure fallbacks, measure tail latency, and deploy gradually with versioned services and rollback capability. Be sure to mention latency, execution limits, supported languages, WebAssembly isolation, state management, service bindings, package size, deployment safety, observability, and when logic should remain at the origin. Question 5. How would you design capacity planning for Fastly's globally distributed POPs? I would forecast capacity by region and workload class rather than relying on global averages. Important dimensions include requests per second, bandwidth, TLS handshakes, cache misses, object size, CPU time, and connection counts. I'd reserve headroom for traffic spikes and loss of a POP, then test failover assumptions. Real-time saturation metrics should trigger controlled traffic shifts, while longer-term forecasts guide hardware and peering decisions. Capacity plans must include security event spikes, not just normal demand. Focus on traffic forecasting, regional demand, bandwidth, TLS and CPU capacity, cache hit ratio, headroom, failure scenarios, autoscaling limits, traffic shifting, and metrics that reveal saturation before customer impact. Question 6. When would consistent hashing be useful in an edge or distributed system? Consistent hashing is useful when requests should repeatedly reach the same cache, worker, or shard while nodes join or leave. Unlike simple modulo hashing, it remaps only a fraction of keys after membership changes. I would use virtual nodes to improve balance and weights for unequal capacity, then add replication for resilience. However, hotkeys can still overload one node, so I'd combine hashing with request coalescing, replication, or load-aware exceptions. Cover minimizing remapping during membership changes, cache locality, virtual nodes, weighted capacity, hotkeys, replication, failure handling, and why consistent hashing does not replace load-aware routing. Question 7. How would you troubleshoot intermittent TLS failures at the edge? I would first segment failures by host name, client type, protocol, geography, POP, and timestamp. Then I'd inspect certificate validity, chain delivery, SNI matching, supported TLS versions, cipher negotiation, and OCSP behavior. Edge handshake metrics and representative client tests help distinguish configuration errors from regional network problems. I would verify recent certificate or configuration changes, roll back safely if correlated, and preserve connection-level diagnostics without exposing sensitive key material. In your answer, cover certificate chains, SNI, hostname matching, protocol versions, cipher compatibility, OCSP, client segmentation, POP or region correlation, handshake metrics, packet captures, and safe certificate rotation. Question 8. How do HTTP 2 and HTTP 3 affect CDN design and performance? HTTP 2 multiplexes streams over TCP, improving connection reuse but allowing packet loss to affect multiple streams through TCP head-of-line blocking. HTTP 3 uses QUIC over UDP, providing stream-level recovery, faster connection establishment, and connection migration. At the edge, I would support negotiation and graceful fallback, monitor protocol-specific errors, and test mobile networks. The best protocol depends on workload and clients, so I would optimize against real-world P95 and P99 latency rather than headline throughput. Mention multiplexing, header compression, connection reuse, stream prioritization, QUIC over UDP, connection migration, loss recovery, fallback behavior, handshake costs, and measuring real user tail latency. Question 9. What is origin shielding, and when would you enable it? Origin shielding adds an intermediate cache layer so multiple edge POPs fetch misses through a selected shield POP instead of independently contacting origin. This consolidates cache fills and can substantially reduce origin connections, especially for globally popular objects. I would place the shield near the origin or along a strong network path, then measure hit ratio, added latency, and shield health. It is not automatically beneficial. Poor placement or a failed shield can create a bottleneck. Explain shield POP selection, cache fill consolidation, origin load reduction, added latency trade-offs, regional placement, failure behavior, cache hierarchy, multi-origin routing, and metrics needed to validate the configuration. Question 10. How would you prevent cache poisoning in an edge service? I would ensure every response variation that affects content is represented in the cache key, while excluding irrelevant attacker-controlled inputs. Host names, query parameters, headers, cookies, redirects, and authorization state require explicit normalization and policy. I'd reject ambiguous requests, avoid caching personalized responses, and validate origin cache control headers. Security tests should target conflicting encodings and header injection. Logging cache decisions and providing rapid surrogate key purges make detection and recovery practical. Be sure to discuss cache key completeness, untrusted headers, host normalization, query handling, response variation, authorization, canonicalization, cache control validation, security testing, and purge procedures. Question 11. Design a rate-limiting solution for a globally distributed Fastly service. I would start with a token bucket keyed by an appropriate identity, such as API key, account, IP, or endpoint. Each edge can enforce locally for low latency, while aggregated state or periodic reconciliation handles global quotas. Exact global limits require coordination and introduce latency or complexity, so I choose approximate enforcement when abuse risk permits. Responses should include retry guidance, and policies need separate burst and sustained limits. I'd explicitly decide behavior during state store failure. Cover identity selection, token bucket or leaky bucket algorithms, distributed counters, approximate versus exact enforcement, synchronization, burst tolerance, false positives, edge latency, client feedback, and fail open or fail closed choices. Question 12. What observability would you build for a Fastly Edge application? I would combine metrics, structured logs, and traces around a consistent request identifier. Core dashboards would show P50, P95, and P99 latency, cache hit ratio, origin time, status classes, bytes, TLS errors, and results by POP, customer, and route. Logs should capture cache decisions and backend selection without leaking credentials or uncontrolled high cardinality data. Alerts should detect user impact, not noise, and every signal should support a practical debugging or rollback decision. Focus on structured logs, request IDs, cache hit and miss rates, latency percentiles, origin health, status codes, POP dimensions, tracing, sampling, cardinality control, alert thresholds, and privacy-safe diagnostics. Question 13. How would you handle a cache stampede after a popular object expires? A cache stampede occurs when many requests observe expiration and simultaneously fetch the same object. I would serve stale content briefly while one request refreshes it, using request coalescing or a per-key lock. TTL jitter and probabilistic refresh can spread work before expiration. Origin shielding further consolidates misses. The design needs lock timeouts and failure handling so users receive stale data when safe, while avoiding a global lock that turns one hot object into a system-wide bottleneck. Mention request coalescing, stale while revalidate, probabilistic early refresh, locking, TTL jitter, origin shielding, hot object detection, failure fallback, and avoiding a single global lock. Question 14. How would you design safe configuration rollouts for edge services? I would treat edge configuration like deployable code, validate syntax and semantics, create an immutable version, and test representative requests before activation. Rollouts could begin with internal traffic, a small percentage, or selected regions, followed by automated checks for errors, latency, cache behavior, and origin load. Every activation needs an audit trail and a fast rollback path. I'd also verify compatibility with dependent services because a valid configuration can still create harmful traffic patterns. In your answer, cover immutable versions, validation, canaries, geographic or percentage rollout, automated health checks, observability, rollback, dependency compatibility, audit trails, and preventing configuration drift. Question 15. How would you make an edge platform resilient to a regional or POP outage? I would design for loss of individual POPs and entire regions, not just machine failure. Health signals should remove unhealthy capacity from traffic steering, with enough reserve elsewhere to absorb the load. Cached content can continue serving during origin problems under carefully defined stale policies, while origin shielding prevents failover storms. Control plane dependencies must not interrupt existing data plane service. I'd test these scenarios through drills and measure recovery time, error rate, and customer visible degradation. Discuss health checks, DNS or Anycast steering, capacity headroom, failover granularity, cache warm-up, origin protection, control plane independence, dependency isolation, recovery objectives, and testing failure assumptions regularly. Question 16. Implement or explain an LRU cache suitable for a high-throughput service. I would implement an LRU cache with a hash map from key to list node and a doubly linked list ordered from most to least recently used. Reads and updates move a node to the front in O, 1. Insertion evicts the tail when capacity is exceeded. In production, I'd define expiration separately, protect shared state with appropriate synchronization, and consider sharding to reduce lock contention. The trade-off is predictable performance versus pointer and metadata overhead. Be sure to mention a hash map plus doubly linked list, 1, lookup and eviction, capacity handling, update semantics, thread safety, memory overhead, expiration, and whether sharding improves contention. Question 17. How would you diagnose and prevent a concurrency bug in edge request processing? I would first identify shared state and define the invariant that is being violated, such as duplicate refreshes or an incorrect counter. Reproduction under load, deterministic stress tests, race detection, and structured timing logs help expose the interleaving. Then I'd prefer ownership or immutable data over broad locking, using atomics only for genuinely atomic operations. Each request should have isolated context, and external coordination needs timeouts. Correctness comes before maximizing parallelism. Cover race identification, shared mutable state, synchronization, ownership, atomicity, reproducible tests, race detectors, lock granularity, request isolation, timeouts, and avoiding unsafe global caches or counters. Question 18. How would you design an API for managing edge services and purges? I would model services, versions, domains, dictionaries, and purge operations as explicit resources. Mutating requests should support idempotency keys, strong authentication, scoped authorization, validation, and clear error contracts. Purges may be asynchronous, so the API should return an operation identifier with status polling or callbacks. Destructive actions need safeguards and audit records. Versioned endpoints and backward-compatible fields protect clients, while rate limits and pagination keep the control plane predictable. Discuss resource modeling, idempotency, authentication, authorization, validation, asynchronous operations, rate limits, status polling, pagination, auditability, versioning, error contracts, and safe handling of destructive actions. Question 19. Tell me about a time you improved reliability or performance in a production system. In one service, P99 latency rose during traffic spikes because cache misses created synchronized origin requests. I measured request traces, confirmed the pattern, and proposed request coalescing plus stale while revalidate. We tested the change under realistic load, rolled it out gradually, and monitored latency, hit ratio, and origin connections. P99 dropped substantially without reducing freshness. I documented the failure mode, added alerts, and partnered with operations to make the mitigation reusable. Make sure to structure the story with context, measurable impact, diagnosis, trade-offs, collaboration, rollout, monitoring, and lessons learned. Emphasize ownership rather than blaming another team. Question 20. Design a globally distributed CDN and edge compute platform similar to Fastly. I would separate the data plane from the control plane. The data plane routes users to healthy POPs, terminates TLS, executes isolated edge logic, checks local cache, and fetches through shield POPs when necessary. The control plane manages versioned configuration, purge propagation, domains, certificates, and telemetry. I'd use immutable deployments, tenant isolation, capacity headroom, and explicit stale behavior during failures. The central trade-off is global consistency versus low-latency autonomy, so critical policies need stronger coordination. Focus on POP architecture, request routing, caching, purge propagation, origin shielding, programmable execution, multi-tenancy, security isolation, observability, deployment control, failure domains, consistency, and operational trade-offs. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.